This allows you to scale applications by building them based on a common programming foundation. OneAPI includes a direct programming language, Data Parallel C++, and a set of libraries for API-based programming to make cross-architecture development easier for developers. Data Parallel C++ is based on familiar C++ and incorporates SYCL from the Kronos group. It allows code reuse across multiple architectures and custom tuning for accelerators. This gives developers the flexibility to break the mold of vendor-specific approaches and opens the door to leverage hardware options not feasible before. With API-based programming, powerful OneAPI libraries are custom-coded for each target architecture to accelerate compute-intensive workloads. With this unified language and libraries, you will be able to code applications that run on multiple types of architecture and deliver performance, all while increasing productivity, saving time, and reducing costs. OneAPI, providing developers the power and flexibility to achieve high performance, cross-architecture, and cross-vendor development. Gain the freedom to innovate across current and future generations of hardware. Test drive OneAPI and the Intel OneAPI toolkits within the Intel Dev Cloud. Your free sandbox to develop, test, and run workloads on a cluster of the latest Intel hardware or software. Or download Intel's beta implementation of OneAPI with additional tools.
So hopefully that's what you're expected to learn about today. If you're in the wrong place, then now's the time to go. Good. So everybody's got sort of a bit of background as to what we're talking about, and hopefully you've seen some of this stuff, had some initial conversations, maybe had a look at our website. So obviously you just saw the URL there, software.intel.com/OneAPI. Obviously that's where you can download the dev kit and the toolkit, I should say. And obviously install that locally if you want. Obviously you can also access the dev cloud through there as well. And obviously there's a lot of documentation, videos, how-to guides and things like that as well. So hopefully, if you haven't seen those already at some stage today or maybe tomorrow, take a look through some of that content too. Just one thing to say, obviously the product is a beta product at the moment. So it was launched on the 17th of November. So it's only like 2 to 3 weeks old. So as I say, because it's in a beta mode, you've got to obviously expect that everything's not fully functioning as you might expect. We're sort of encouraging customers to start looking at OneAPI in terms of understanding what the tool is, what the approach is we're doing from a heterogeneous programming environment, and then really just sort of get a feel for it, see how it works for you, have a look at some of the toolkits, some of the documentation.
Can you show me the first slide with password?
If you speak to somebody at the back, they'll probably help out. So.
Okay.
Can you put the normal slides back up, please? So yeah, so as I was saying, it's a beta product, so obviously understand that. If you do find there's some issues today for whatever reason, obviously just let us know. We're obviously keen to get feedback from people, so obviously please tell us what you think if you do spot any bugs, anything like that as you go through any of the labs. Obviously there's a lot of content to go through as well, so please bear with us as we get it up and running. Given we've just had a conversation there about Wi-Fi, I assume everybody's got access to that code. If you don't, then obviously just let us know again. It's at the back, it's on the screen at the back, and obviously here on the left. So if you do need to access the Wi-Fi, it's there. The agenda for today then, so obviously just doing a quick welcome now. We're then going to have an introduction to OneAPI, so Mike's going to step up in a couple of minutes and give you a more verbal introduction to OneAPI, going through what it is and all the various toolkits and everything that's supported inside there. We're then going to look at the offload advisor, which obviously how to decide which parts of the code need to be offloaded. And we'll have Cedric presenting that for us today. A break mid-morning, coffee, snacks, whatever we need to do. 11 o'clock, we're then going to go into an introduction to Data Parallel C++, obviously the vector addition samples and device selectors, and there'll be a small lab as part of that one as well. So obviously you start accessing the dev cloud, there'll be some Jupyter notebook types instructions and things of the labs, how to follow, etc. But again, Cedric will be able to explain all that to you. 12:30 to 1:30, we're planning on having lunch. Obviously they'll just be served outside, just pretty much sort of sandwiches, salad type stuff as well. So that'll be just served outside there. Obviously drinks and everything supported with that. And then we'll be back in again at 1:30. And then we've got a speaker, Graham Mackenzie, who's going to come in and talk to about the FPGA portion, so how you obviously develop code to run on FPGAs. A break following that, and then obviously we'll go into the case study at the end, which is a high performance computing application sort of workload. And so we have a case study around that, which obviously again with some more hands-on work, which then pretty much takes us through to the end of the day. At the end of the day, we've then got some drinks and stuff outside. So again, we strongly encourage everybody just to hang around for half an hour if you can. Obviously, I do appreciate some people need to get away, but if you can hang around, we'd really like to get some feedback. There are quite a few Intel folks at the back of the room who will obviously be around, and we really want to get your feedback. As I said before, because it's a beta product, the feedback's really important to us to make sure we're actually producing the best product that we can. So please try and do that for us. In addition to that, you've also been given a survey when you register just outside. You should have it all in front of you at the moment. If you wouldn't mind filling that out. Now, I know there's probably quite a few questions in there, but it's only sort of 2 pages. So if you don't mind filling that out, that'd be absolutely fantastic. There is a TileMate as a free gift for anybody who obviously completes it and hands it in for us at the end as a bit of incentive. I think there's some t-shirts and notepads as well. So again, obviously welcome to those two. But again, ask questions throughout the day. Cedric's our expert on OneAPI, so please take advantage of him while he's here. I think I'm pretty much be able to cover most things that you're going to be able to ask. So really sort of pick his brains, and if you've got any questions around the tool, how it works, some of the technology and things, then please do ask. And then, as I said before, just please stay towards the end if possible for some networking and drinks. So Mike, you want to come forward and get your PC set up? So again, the software.intel.com/OneAPI is our resource on our Intel Developer Zone. Again, please go and take a look at that at some stage. Like I said, there's lots of videos. Go to our YouTube channel as well. There's lots of great videos on there, show you how to use things and get set up and what have you. And yeah, so I hope you all have a good day. If you need anything, by all means, we've got some staff outside from logistics in terms of where bathrooms are. If people need that, if you need anything else from an Intel perspective, I'll be around. As I said, there's a bunch of Intel people at the back. We've all got our names and Intel written on the badges, so you should be able to identify us. If you need anything, have a good day. Over to you, Mike.
Okay, let's go ahead and get started. Good morning, everyone. My name is Mike Lee, and I'm the Senior Product Marketing Manager for the Intel Software Developer Tools. Just a show of hands here, Parallel Studio XE. Who uses tools out of the Parallel Studio XE? Okay, a few folks. C++ developers? Okay, Fortran? Oh, okay, very cool, very cool. All right, so and Parallel Studio XE is actually the tool suite that I'm the product manager for. I'm also the product manager for the Intel MPI as well as the Intel Trace Analyzer and Collector tools. But today, what I'm going to do is I'm going to tell you about OneAPI. And I think that video is going to be a lot more polished than me, but what I'll do is I'll walk you through the slides in this next 25 minutes or so and give you a little more in-depth dive into what OneAPI is all about, the different toolkits that that are in beta today, and then what you'll see this afternoon from my colleagues to dive more into the data parallel C++ language as well as some hands-on experience. Okay, so as the video said, the big challenge now is that we have so many different workloads. AI, obviously, you can't turn the corner and not get asked about AI if you're a programmer or if you're going to use AI and apply it to some industry that you're in. So what has happened is a lot of different architectures are out there. GPUs to speak of, vector, and then for scalar, primarily that's CPU. But then again, a lot of the CPUs also have vectorization in them as well as our modern Xeons do today. And then of course there's matrix like AI hardware, and then of course we have spatial, which refers to FPGA. But the key thing is that there's really no common programming language or APIs for any of these things, right? And the thing is that the tools very different from what you'd use to program to do C++ and Fortran versus what you would do for Verilog and VHDL, for instance, or even something like CUDA, for instance, in the GPU world for what NVIDIA has. So what that means to you and your companies is that you're investing a lot of time, energy, and money to basically develop for these specific platforms. And it basically, that means you're investing, across all these different architectures, and it's basically diverse. So, and that basically brings a challenge, right? Because when you want to scale it forward, sometimes you can, sometimes you can't. If it's not built on standards, you're basically stuck. So what we've done is basically at Intel, we've said, hey, let's look across all of these architectures. What can we do to basically unify this programming model to basically simplify development across all of these different architectures? And that's what brought about OneAPI. So the key here is that basically we're driving an industry initiative. So this is not just Intel. I'll show you a slide of a bunch of logos that we have of companies and institutions that are backing our efforts here. But basically Intel will implement the first spec of this, and we've already released the specifications for OneAPI. That's available now, I think, at oneapi.org, I think that's right. So you can see the full specification there. We also recently introduced what's called the level 0 driver specification, so that's out there as well. So the key thing about OneAPI is that basically we want to basically have this, uncompromised native high language level performance, okay? So, and again, we want it to be based on industry standards and open specifications. And I think as you heard the video say, it's based on basically SYCL, which is part of the Kronos group. Who here has heard of the Kronos group? Very good, okay. And also to preserve legacy, we're also, of course, making this interoperable with HPC programming models. So again, my background is HPC, so for those of you who are doing OpenMP, you'll find that we have support for that as well. All right. So again, the initiative is really to drive an alternative to a single vendor solution. So we're really driving this to the industry, and it really is about driving. I would say it's sort of like a common abstraction layer between the hardware and the software. So as this will evolve and we do it right, this is actually good for the entire industry, not just Intel, but the entire industry. So that allows silicon vendors to really innovate on the silicon level, and then as long as they're basically defining it to use this OneAPI specification, basically you as developers get all that benefit. So it is based on data parallel C++, as was mentioned, is basically based on C++ and SYCL. The direct programming language for this will be data parallel C++. And then we also have a number of libraries that we're basically bringing to this effort as well. And I'll show you those in just a moment. But the key thing here is that those libraries, if you're familiar with MKL, who here uses MKL? A few folks, okay, very good. So basically through API programming, so the beauty of libraries is that you just need you get the new library, you basically relink the latest library, and you get the latest all the great performance out of our latest hardware. So basically, again, we're using this promoted across the industry to get this open standard and community working, so that it enables you to reuse your code across these different architectures. Okay, so let's talk a moment about data parallel C++. Right, it's standards based and it's cross-architecture language. So the key thing here is that basically it is built on top of C++, and then basically on top of SYCL, and then Intel's adding the extensions to it. So the key thing here for us to do is that basically the extensions we're adding, like unified shared memory, we're basically taking those and actually putting back into the SYCL standard. Okay, so we're upstreaming all those changes to the Kronos group to basically continue to drive this forward. Ultimately, what we'd like to have this be, with the community driving this, is to be part of the C++ standard. We know this is a long road. We know that basically this is a tough effort, but I think it's one that basically is good for the whole industry. Again, not just Intel, but good for the whole industry. So the libraries. So here are the libraries we have. Basically, we have a math library, which is going to be based on MKL. We have the threading library based on TBB, the thread building blocks. We have a data parallel C++ library, analytics, DNN, and machine learning. I'll talk more about these in a little while, but then also video processing. So the key here is that you don't see libraries that aren't already standards. And what I mean by that is you won't see MPI here, right? Why? Because MPI is actually a standard already. So where there's already a set standard and that there's a body driving it, there's no need to do that. So, but where there isn't, and we feel, and as this effort grows and the community grows, I think you can expect more API-based programming libraries to come on board for OneAPI. Okay, so as my colleague Scott said, we're in beta right now. So it was released November 17th, and basically, the OneAPI product basically is delivered through what we call the base toolkit or the core toolkit. And so with it, basically we have the Data Parallel C++ compiler. We have the libraries that I just mentioned. We'll have a set of analysis and debug tools, which if you're familiar with vTune and Visor, you'll see those this afternoon. Those have been augmented and enhanced to basically be able to target alternative architectures such as accelerators, GPUs, and FPGAs. But then we also have a compatibility tool. So this compatibility tool is basically help you migrate your code to basically migrate your code to Data Parallel C++. So as you continue to develop, through the Data Parallel C++ standard, you can just basically roll your code forward. And I'll talk more about that in just a moment. So as I mentioned earlier, there's an ecosystem that's basically doing a lot, that have signed up to support our effort and drive for OneAPI initiative, and these are just the beginning. So as we continue to gather more companies, and we'll announce them, these are the folks that are working with us to basically drive this initiative forward. So let's talk about the OneAPI toolkits for just a moment. So you can see the base level toolkit, and again, I'll go over the details on that in just a moment. But basically what we have then is toolkits that build on top of it. So we'll have the OneAPI HPC toolkit, we'll have the IoT toolkit, the Deep Learning Framework Developer Toolkit, a rendering toolkit for those of you who are doing visualization. And then of course there's toolkits that are also associated, system bring up for those of you who are doing system development. OpenVINO if you're doing some optimizations around deep learning networks, and then of course the AI analytics toolkit. But I'll focus on the four that are the five actually above those other three. Okay, so let's just talk a little bit about the OneAPI based toolkit. So sorry, I know this is a lot here. So this is the core set of libraries and tools that are basically going to be used to develop for CPU, GPU, and FPGA. So the idea here is basically this core is the broadest set of tools that are applicable across, horizontally across development. And then all the other toolkits, as I mentioned, like the HPC toolkit, will be add-ons. So what you see here, basically on the direct programming side, what is included here would be the Data Parallel C++ compiler, and then we'll have the compatibility tool. We'll also have the Intel distribution for Python, and then we'll have the FPGA add-on to the OneAPI base. So that is actually another kit that adds on to that. And then through the API-based programming, I won't read the list, but there's a number of libraries there that I'll touch on a little bit later. And then on the right-hand side, for those of you who are familiar with vTune, like I said, an advisor, and then of course our GNU debugger that's been enhanced. These are the set of tools that you'll find in that core base toolkit. So as my colleague Scott mentioned, you can actually get that now if you want to get that, you can actually download it, install it locally, or you can actually run it in the dev cloud. So anyway, so this is basically all the what's inside the base toolkit. So let's just talk about the Data Parallel C++ compiler for just a moment. So here, basically, it's based on SQL and C++, and basically it's built on top of Clang and LLVM. So Intel has done a lot of work there to basically advance and upstream work to Clang and LLVM, and then basically runs on top of the Data Parallel C++ runtime, which basically targets the various accelerators that are available. I mentioned the Data Parallel C++ compatibility tool. So what that tool is intended to do is basically take CUDA code that you currently have today and basically create a Data Parallel C++ version of it. It gets about 80 to 90% of the code, and for the pieces that it can't get, it'll basically give you reasons as to why it couldn't do it, and basically some of the things you'll have to do by hand to get it all the way through. The idea is that you're going to actually just use this one time once you get your code from CUDA into Data Parallel C++, that you'll take that Data Parallel C++ and continue development there to target the different architectures that are available from Intel and hopefully from other silicon vendors that join our OneAPI initiative. The Data Parallel C++ library, basically it's a set of optimized algorithms, 75 of them based on top of C++ 17. And again, if you're familiar with Parallel STL, you'd be very familiar with these libraries. And then it also has support for Boost Compute. And again, it's integrated with our compatibility tool. So video processing library, if you guys are familiar with the Intel Media SDK, that's included in this. Again, this is where standards have not been set, and this is where Intel is driving these to be standards. So basically, the libraries that you'll get here are APIs that basically will be able to target CPU and GPU moving forward. And then here's our deep neural network library. And again, here, basically, we provide you with a set of a library that basically has instructions that are optimized for Intel architecture. So basically, it's the same API for both CPU and GPU. Again, going back to the, you're programming to OneAPI, a library that basically allows you to target both CPU and GPU. And as we move forward, and it makes sense to have that same functionality available on an accelerator like an FPGA or other accelerators that Intel will bring to market, those will become available too. So here we have the collective communications library. If some of you are familiar with a library called the machine learning scaling library, it was based on an MPI implementation that Intel had. It's in GitHub. Basically, if you're doing framework development, it's like an AI framework development, this would be a great library for you to use to basically distribute out your deep learning training. Okay, so vTune Profiler. Again, who here uses vTune? Show of hands. Great. Okay, so Noah love vTune. It is probably the most powerful profiler on earth for Intel parts and for CPUs. But what we're doing is that we're extending that for GPU as well as our FPGAs. So all the experience that you've had with this tool, again, it'll be extended across to those other architectures, help you understand where you can, optimize your offload as the accelerators are looked at as offload compute elements, and then basically, do a wide range of performance profiling across all these different architectures. And of course, we basically support data parallel C++ with this, and C++, Fortran, Python, Go, and a mix of them actually. And then Advisor, I think you guys are going to get hands-on this afternoon. So Advisor has been enhanced to basically help to analyze your code and help you understand where there might be portions of code that are basically worth to offload. So it'll walk you through that. And if you haven't used it for CPU development, you definitely should give it a try. It'll help you understand where your code is and where there's opportunities to optimize using such analysis such as Roofline if you haven't used that. And then it also does vectorization advising as well as threading advising as well. And then of course we have the trusty old GNU debugger, and this is basically our version of it. So this is included with this has been included with our compilers for the last number of years. Before we had the Intel debugger, but now we switched over to GDB. And then here we have the OneAPI for FPGA. So this is basically data parallel C++ coding for spatial architecture. My colleague Graham will be talking about that more this afternoon, but he'll walk you through the process of basically taking data parallel C++ and going through and to target an FPGA. And let me just quickly run through some of these, these other toolkits. As I mentioned, for the HPC toolkit, that's an add-on. As you can see here in the white, basically are the additional. So if you're doing C++ or C with OpenMP, that is included in this toolkit, as well with Fortran and OpenMP. And then of course, on the API side, we add in the Intel library, the Intel MPI library. And then on the analysis side, we have the Intel Inspector, which is a memory and threading analysis tool. And we also have Trace Analyzer and Collector, which is an MPI it's an MPI communications analyzer. And then of course we have Cluster Checker, which is an expert system that basically helps you monitor the health of your system, your cluster system, and make sure that it is running at its top performance. And again, mentioning the Intel Fortran compiler and the C++ compiler, we've continued to lead the way here, for the Fortran, especially for the Fortran compiler, but then for C++ as well. Intel's been developing compilers for over 20 years, and we continue to deliver peak performance on our Intel Xeon processors as well as our Core processors. And of course, we support the latest standards such as OpenMP. I think we're up to OpenMP 5.0 now, and I think there's the technical report 8 that we're starting to implement. And by the way, if you have a Gen 9 GPU, we actually support that with OpenMP offload now. So if you have a laptop or a desktop that actually has support for the Gen 9 graphics, you can basically use that as a compute element to try data parallel C++ on, and as well as OpenMP offload. And then IoT toolkit, again, this looks more sort of towards embedded development. Again, I won't dive into details, but basically almost all the same, minus the Fortran pieces. And then the API rendering toolkit, for those of you who are familiar with doing visualization using things like Embry or OpenSWR or Osprey, those were visualization libraries built specifically for CPU. And basically it gives you high fidelity, high performance visual applications. In other words, you don't need to move your data over to a GPU to visualize it. You can actually render it using very effectively using CPU. And then here we have our our deep learning framework developer kit, and as I mentioned earlier, it includes the deep neural network library as well as the collectives communications library, or the machine learning scaling library. And then our AI analytics toolkit. This is more and more for usage of AI analytics on Intel architecture. So here we have the Intel optimizations for TensorFlow, as well as our distribution for Python and also PyTorch that we support here. So again, for those of you who are doing some AI work on Intel platforms, this is a great library to have. And then of course the OpenVINO toolkit for those of you who are looking to optimize and do optimize neural networks as well as do computer vision. A great toolkit to have. And then let's see, lastly, I think this is the last one, system bring up toolkit. Again, for those of you developing and designing systems and bringing them up, this tool helps you do system debug, trace, power thermal analysis, and basically on top of the drivers and BIOS and firmware. So we're bringing this to market. We know there's going to be a lot of work, and we know that this takes an ecosystem to get data parallel C++ up and running on this OneAPI initiative. So we'll have a number of developer programs of which the dev cloud is one, and we'll have academic programs, and then we'll also have development kits. And then as far as supports go, there's active OneAPI forums now. So if you start using it, you have questions, basically just go to the forums, post questions, and you'll get answers. They're monitored by Intel software engineers, and you'll get your answer. And then as far as ecosystem engagement goes, that wall of logos that you saw, that continues to be developed out, right? And then also Intel participates in the standards bodies, but then also, basically we're working with third-party solutions, other ISVs to make sure that their software will be supportive of our OneAPI initiative. And again, I think my colleague Scott had mentioned DevCloud, get up and running in seconds. Basically you sign up for an account and you can basically get running. You don't have to download and install locally. You can use it up there. And I'll have to say that, the DevCloud will also be the first place that you can actually get our discrete GPUs. So when those are ready, and we basically will install them into our DevCloud, you'll have access to those. So the summary, call to action, right? So if you're going to the heterogeneous world out there to take on various varied workloads more effectively, and data parallel C++, as well as the OneAPI initiative helps drive that forward, helps preserve your investment. So really, it's about getting started today, understanding where you can be effective in terms of understanding what to offload. And then starting to learn a language that'll help you basically scale forward to offload that to a variety of acceleration technologies. So get started with it today. And that's it. And this is the legalese stuff. So any questions? Otherwise, I'll probably turn it over to my colleagues so you guys can get started getting your hands dirty and learning about the latest and greatest for data parallel C++. Yes, question? Later, right now we're basically on Windows and Linux first, and then Mac Mac is part of the operating systems that will be supported. Okay.
Do you have searchable encryption libraries?
I'm sorry?
Searchable encryption libraries?
Encryption libraries?
Yeah.
Yeah, through IPP, the Intel Performance Primitives.
Normal encryption or searchable encryption?
So the question was do we have
searchable encryption?
Searchable encryption?
Yes.
I'm not sure about that. I'll have to get back to you.
Okay, thank you.
Okay. Another question? Yes.
Is it license free?
Yes, it is license free.
But then what about the other?
The Parallel Studio tools today are our commercial tools. We will have commercial versions of these tools as well. The tools are beta right now. The tool, as we call them, the toolkits. So they're beta right now, so you can freely use them. But moving forward, as we announce product plans, those will be forthcoming. Okay. Any other questions? Okay, if not, I'll turn it over to my colleague Cedric. Thank you, guys.
Good morning, everyone. So that's the second day for me, maybe for some of you, some of you guys here. So we tried to make an agenda. Actually, it's a bit different from what was presented at Supercomputing a few weeks back. So I don't know, by the way, if some of you were at Supercomputing and did attend the training on OneAPI. No one? Perfect. No, so that will be new stuff, so that's probably better. So actually, there was a training at SC which was covering the whole data parallel C++ language. You still have access to that. Actually, I will show you how to get this training if you want to practice even more than what we are going to do today. But the agenda today is a bit different because we wanted to have something more practical for you. So basically, how do you start with your current applications that probably runs on the CPU at some point? And how do you detect what you should offload? And how do you basically move this code to the GPU or to an accelerator with data parallel C++? And so this is the reason why the first presentation this morning is not about DPC++. It will be about something called Offload Advisor. So this is part of OneAPI products. And this tool will help you to detect what part of the code should be offloaded to an accelerator. And also it will give you some performance expectation on this given accelerator. So this is why we are starting from here. So let's try it. So that's basically the agenda. So you will have access to this presentation. The presentation is basically an introduction. Then you will have all the command line tips to be able to reproduce what I will show you today. Then I will just give you some insight about how we compute the performance modelization. So this is not a simulation with this tool. So you take your application on the CPU and then we provide you some numbers on the GPU without running it. And I will just try to explain basically what we are doing. I think it's important to understand. And then at the end, I will also show you that we can run the roofline model on the GPU. So that's already working with Advisor. So who doesn't know Advisor at all here? Okay. So I will just start even before this slide. So Advisor is a tool that is mainly used for enabling your vectorization in your application. So we have different analyses that will look at your code, check for every loop if the loop is vectorized or not vectorized, give you insight, and what you should do basically to improve the performance through the vectorization. And they also have the roofline model implementation, so you are able to characterize your application, see basically how far you are from the best theoretical performance for your given application on a given platform. And now there is this offload feature. So the idea, you start with a baseline, you have your code on the CPU, you will run several analyses that I will detail later. And then at the end, you will have this kind of report, and we will go through this report where you will see the performance on the GPU, which part will still remain on the host, on the CPU. You will get some indication about what you should offload, what you should not offload on this part, and also some insight about what is going to limit your performance on the device. So that's very useful actually to start working now, even if the hardware is not available yet. So far, if you want to run a Float Advisor, you have two different ways to do it. You need a CPU application, and your CPU application can be in C, C++, Fortran, even Python actually will work at some point. And then from this application, we are going to compute what can be offloaded, generate some acceleration number, and we take basically the GPU estimation plus the CPU measurement, and we provide you some numbers about the elapsed time when you will use this accelerator. The second way to use it is if you have an application still CPU based, but with some parallelization already implemented. So it will work with DPC++, OpenCL, and OneAPI. So if you are using DPC++, that will make sense later, but if you want the advisor to work, you need to use the target host, otherwise it will not work. So that just, and then this is working, so I don't know, yeah, the pointer will not work. So this is working exactly the same way, so we have some measurement on the CPU, we are keeping this, and then we are using the GPU expectations to compute basically the runtime. So what is going to come next is actually this part here. So we are going also to support running on the CPU plus the integrated GPU. So you know that on those laptops, for example, you have integrated GPU. So in this one, this is the Gen 9. If you have a brand new laptop, I think this is already available, you might have a Gen 11. And then we will be able to use an application with Data Parallel C++ or OpenCL, for example, that is using both CPU plus GPU, run a Float Advisor, and then get your performance expectation. So that will also work probably for the next release, or if not the next release, the one after that. So that's the report in detail. I will just check the time. So I think I need to stop at 45. So the first block that you have in the output, so once you've run Advisor, generated the output, it will generate an HTML file. So that's pretty interesting because if you play on some machine that is not local, then you just have a single file to copy back and to open on your laptop. You don't need anything, you don't need the source or to bring back the sources. So that's very efficient when you want to use it. And then when you open this report, you have, so this first section is about performance expectation. So what do you see here? The first part here, this is the original time. So that's basically how much time you spent running your application on the CPU. And then the second line here, this is the expected time once you offload some work on the GPU. So Advisor will detect basically what should be offloaded and will compute this time and provide this time to you. So for example, you see that on this application, it spent 13 seconds or 14 seconds almost on the CPU. And if I'm using a Gen 9, then I can expect to shrink this time to just 1.6 seconds. Okay, so you see also the number of offloads. It means that how many loops you are going to offload. So in my case, I'm just offloading one loop here. You get some speed up, so speed up of the accelerated code. So that means how much gain you will get on the part that goes on the GPU. Overall speed up, so under slow speed up, this is the overall speed up on your application. That's the proportion of the code that will be offloaded. So this is a very computing intense code here. So I'm basically offloading 99% of the runtime. So that's the reason why I get very good speed up. So the second part, which is actually pretty important also, is about what you should offload. So that will give you the loop, the line, and also some metrics. So you have many more metrics than that. I will show you a report at the end of this presentation. And then you know basically where to start. So that gives you some insight about what to do next. That's really the idea here, to help you move your code to the GPU. You have also this part that will tell you what is going to be your limitation on the GPU here. So if I'm doing this offload, what I can expect is that on the Gen 9, I will be limited by the LLC bandwidth. So that will be my limitation. If I'm doing the offload like in the easiest way possible. So then I can optimize, of course. But if I'm just keeping the code like that and putting it on the GPU, I can expect to get some problem of bandwidth on the LLC side. And then you have another section, which is what are the loops that should not be offloaded? And there might be many reasons for that. You might want to avoid doing offload because that will not be profitable, meaning that you have to pay too much tax, for example, to copy the data on the GPU, and you don't have enough iteration. It might also be because you have dependency in your loop, data dependency. So if you try to parallelize basically this section, you are going to break your results, and you don't want to do that. So there are many reasons here. An advisor will provide you some insights. So sometimes some of those non-offload loops can be optimized in a way that will be at the end a good fit for offloading. For example, if you see that you have several loops, like several for loops embedded, an advisor reports you that the innermost loop, for example, is not profitable because you don't have enough iteration. Maybe what you can do is merging some of those loops to add actually more iterations. So it doesn't mean necessarily that you won't be able to offload this part like never. It means that in this state, you need to work at some point. So that's the idea here. So now I'm just zooming on each of those parts. So basically in the report, you have some tabs here, and you can click on those tabs. And the second one, so the first one that I showed you was the summary, and then the second one is the part where with the regions that you should offload, basically. So that will list all the loops here. You click on one loop here, it shows you the code, and the gray part is basically where you should start the offload. So all this gray section here should run on the device. That's how to understand that. So then that's your job to use TPC++, OpenCL, whatever, OpenMP offload, also OpenMP target, to make this part run on the device. But at least you know where to start. And then you have many metrics, so I will show you in detail, but you have the number of LLC accesses, the flops, the bandwidth, many things that you can read here. So the second part here, so this is the non-offloaded regions, and that will give you some insight about why it's not interesting. So for example, this one is not profitable. So I guess that if I'm scrolling here, I will get information about maybe few iterations or something like that, so that's not interesting. Then for the second one, it tells me that the total time is too small to get some really reliable information. So, and then you could also have some dependency issue. So there are no dependency here in this screenshot, but you might get some dependency issue. And it will tell you, don't do it, otherwise you are going to mess up your results. So no questions so far? So you also have access actually to the program tree, so you can extract this information also with Offload Advisor. So it's not something that will change your world, but at least you can understand which parts, and very easily which part of your application are going to run on the device. So how to understand that? Basically, all that is in white will run on the CPU. All the parts that are in gray, so here, and many others here, it will run on the GPU. So that gives you some indication about the proportion, basically, of your code base that will run on the GPU at some point. So that might be pretty horrible. If the application is big, you might end up with something a bit crazy. But at least you can do it. And so now, more pragmatical part of the presentation, how to use it, how to do it. So first, you don't need specific compilation. You just need basically to have the debug information. So -J, otherwise you will get some performance prediction, but you will not get any interesting information like what you should offload. So if you don't have -J, then you will just get partially the information. So what is also important is when you use Offload Advisor, try to use the compilation flags that you are using for your application, like for production or whatever. So if you are using O2, keep O2. You want to try to offload the application in the state you are using it. So what might help at some point is to use no IPO, otherwise it's more difficult for advisor to track down the different informations. So this is the only constraint at some point. So you might use IPO. If you get weird results, then try to disable it. So that's really the only tip at some point if you get some strange things here. So how to start? You need first to source OneAPI environment. So you will not do it completely today. So there is a script that we will detail when we are going to use the cloud. But if you install OneAPI, so you can download it if you are registered to basically the cloud. You can download it and you can install it on your machine. It's basically like Parallel Studio, same kind of installation. And it works exactly the same way, so you need to source, and you need to source basically this script, setvar.sh. So once you have done that, starting the beta 3, you have some environment variable that is set, which is called APM, and that will actually contain all the path to advisor performance model. And this path is important because this is what we are using to generate the performance prediction. So in this directory, you have some scripts. You also have some performance description of the hardware, of the target hardware. So you won't be able to read it because this is some binary files. But this is where you have all those things. And then we can start. So there are many ways to run Offload Advisor. The easiest way is to run this script here, run oa.py. So this is a batch script, and this script is going to run all the analysis for you. So you don't need to do anything, you just need to set it up. So you have few parameters. One that is important here is to specify which hardware you want to target. So that might be Gen 11 if you want to do the performance prediction for Gen 11. And then you need to provide an output dir, and you also need a path for setting up the batch script, basically. So that's basically it. And then at the end, you put your application with your parameters. And that's how it runs. So then you can go grab a coffee, wait for a few minutes, and come back. And at the end, you will just need to run this script here, analyze.py. And this script is going to generate the output. So basically here, you run all the analysis, and here you generate the HTML files. So what is basically run behind? So you have your application with -j, okay? And then you run the script run_OA. So first what it's going to do is run what we call the survey in Advisor. So the survey, this is an analysis that has almost no impact on your performance. It's using sampling, and it's using sampling just to time your different functions, your loops. So we just want at this stage to get your application in the way you are using it, basically. Then there is, in the script, there is some additional script that is going to do some markup. So basically, the script is going to select some loops, so the most important loops at some point, and they are going to mark those loops. And the markup is going to be used actually for some of the other analyses that will be run. So then you have a second analysis, and this analysis is actually doing some of the stuff here. This is called the trip counts analysis. So it's basically instrumenting your application. So looking at what is executed. So it takes your binary, read it, and then check every operation, every assembly operation that you are executing. So this is not based on the assembly generated by the compiler. It's really dynamic. So it really look at what you are executing. And then it will count the iteration. It will count the flops, floating point operations. It will count basically the memory transfers. And also it will add some cache simulation. So the cache simulation is a way for us to get information about how many misses you have on the L1, L2, L3, and all those information are used then to get some insight about how much painful it's going to be for doing the offload, how much tax you are going to pay basically if you want to move your kernel on the GPU at some point. So this cache simulator is basically set up when you are using, I can go by option from one slide, that would be easier. So the cache simulator is set up when you basically set this Gen 9, Gen 11. So the configuration of the cache simulator will change if you change this setting here. We want to do the cache simulation targeting the device, basically. And then after this step, so this is one single analysis that does everything here. And then you can add, so that's not mandatory, but you can add the dependency analysis. So it's not mandatory because this analysis takes a lot of time. Like you can expect 20x slowdown or something like that. The main reason is because this one is checking all your memory accesses. So this is also doing instrumentation, and they check all your memory accesses, so you have some time that is lost here. And they want to detect if you are doing some accesses close in memory, and if you enable vectorization or threading, then you could basically get some troubles. So this is the reason why this analysis is slow, but this is kind of important if you don't know what you can basically parallelize or not parallelize. So I would really suggest to run basically this analysis by default. And once you have done that, then you can run the analyze.py, which will generate the output. So then you will have the report.html, which is the main report. You will have some other files like the program tree. This is the one that I showed you with the tree here. And you have other files that are generated that you can use, for example, with JSON or whatever format. So I told you that dependency analysis was not mandatory. So how to remove it? You can remove it directly from the run_OA. So if you want to do some kind of quick test, you just add this option, -c basic. And -c basic is going to run everything except the dependency analysis. And then what you need to do when you run the analyze.py, you need to add this option, assume parallel. It means that at this stage, advisor will assume that your loops are parallel and that they can basically offload all of your loops. So of course, it will also impact the performance prediction, because if you have some dependency, you will get some performance prediction that might be too optimistic at some point. But that's up to you to remove the dependency analysis and to basically say that you want to run the performance prediction on everything. So there is also a way to mark up some loop, actually, and to tell advisor that even with the assumed parallel, some of the loop needs to stay on the host, basically. But this is more advanced, so if you have some question, you can just contact me later. Okay, so now if you want to get a little bit deeper with this tool, and if you want to do the analysis by yourself, so the different analysis, and if you want to change those analyses, it's a bit difficult to remember all the command lines, options, and things like that. So an easy way to do it, you set up the run OS script.py, and then you had the -- dry run option. And if you add this option, it will not run advisor, it will just give you the command lines, the different command lines that are used. So you can just extract those command lines and run it yourself and change some of the parameters if you want. And that's very easy to do. So the different analysis now, I told you earlier we start with the survey. So that's how we basically run it. So advisor CL, that's for command line. Then we collect survey. So we have few options, but they are not mandatory here. What is important is just to specify actually the project directory at this stage, and then your application with the parameters. So this one is pretty easy to run. It's doing sampling, it's doing some binary static analysis. Actually, it will give you also, if you open Advisor in the GUI, it will give you some insight about your vectorization. So you can also check at this stage the vectorization. Then the second analysis, and this is the one which is the most difficult to set up. But if you are using the dry run option, you will get some of those parameters, if not all actually. So this is the trip counts. So the trip counts, we are counting the iterations, and we also add the minus flop option to also count the operation. So how many flops you are doing for each basically loop, each function, and everything. We also need to enable data transfer analysis, which will be used to compute the tags for offloading the data on the GPU. So there are some other parameters that are not actually mandatory. And then this is enable cache simulation with the cache configuration. And this is actually the part that is kind of painful if you want to do it by yourself. So that's the reason why if you want to use this independent analysis, just use run OA.py with dry run and you will get this setting. So you just have to copy paste it. And this is the cache configuration here for the Gen 9. So that will do the trip count, count the operations, evaluate data transfer, basically. So you can expect something like 10x speed down here. And after this analysis, when we are basically merging the data, we are taking the time from the first analysis. So that's the reason why we have the survey. It's just to get the time from a run that is not impacted by all those crazy things that are happening here. Then if you want to run the dependency, so Advisor CL again, collect dependencies. And what I'm using here, I'm not actually using the parameters by default from the run OS script. I'm saying basically to Advisor, I want to profile for dependency all my loops that are running for more than 5% of the elapsed time. So saying that I don't care about the other one because I will probably not offload them. And then there are some other parameters that are still not mandatory here. So that's how you run it. So that's the different analysis, checking the time. Okay, and then you need to run the analyze.py. So once you've run all those things, then you run the analyze.py, and there you need to specify what will be the target hardware. So, and then you need also to make sure that if you want some good prediction, you need to make sure that this target is the same as the one you use for setting up the cache configuration before that. Okay, so no questions so far? So now we'll try to explain how we get this performance prediction. So this is what we call first order analytical modeling. So basically we compute throughput model, then memory subsystem model, and then we try to add to that offload taxes. So let's say that you have one application and you have two different functions or loop or whatever. So the first one is spending this time, so this is the time here. The first one is spending this time, and the second one is smaller and is spending just this time. The first thing that we are doing here, we assume that your application is bound by computation, which might not be the case. But this is the first assumption that we are doing. And then we say, okay, so we have that many flops. What should be the elapsed time if we can use the GPU here, which might have actually a more flop power? And then in this case, for example, we shrink it to this one here, and we shrink this one to the orange part, okay? Then we do a second assumption, which is what will be the elapsed time if we are bound by memory, by data transfer at some point. Okay, so we do the same. We have a different number here, a different runtime here. And then we also had offload taxes. So, you know, we run this cache simulation. We have many data on data transfer. And then we need to add this information to the output. So in that case, maybe for this one that will be this part, and for the other one that will be a bit more, okay? And then what we are doing is that for each region, to compute the time on the accelerator, we take the maximum of those two here, and we add the kernel invocation plus the tax for the data transfer. And we do it for all those different regions. And at the end, you will see basically something like that. So for example, for the first region, for the X1, you see that you are getting some speed up. So this one will be interesting for offload, and that will appear in the top offloaded loops. And this one here seems not interesting. So this one will appear on the other side saying you should not offload this loop because this is not interesting. No questions so far? You are quiet. And now this is just to show you what we are doing to get the whole performance prediction. So we are just summing up all those different loops, and at the end you have some elapsed time on the device. So that's how we do it. So this is not a simulation. It's really different from like a cycle accelerated simulator. So the main difference is that on the cycle accelerated simulator, if some of you are working with co-design project, for example, so with us, we can do actually some cycle accelerated simulations. It's really, really painful. You need to extract few millions of instructions in a given loop, just extract those instructions, then run it on the simulator that can spend like 2-3 days for just few lines of your code. And then based on the result that we have some cycles spent for the simulation, and then we try to extrapolate the overall performance on the whole application. So that's very painful. Here, the concept is completely different. We don't extract anything. We just use your application the way it is so far. You run it, it takes some time, but it's not 2 days. And then you get some performance expectation on the whole application. So that's, for a user standpoint, it's much easier to use actually. Okay, so we also have, so this is actually starting beta 3. So there are some issues with DevCloud actually. You won't be able to extract the roofline model on the GPU on DevCloud because some driver problems, they are going to fix it. But so far it's not possible. But at least if you install it by yourself on your machine, you will be able to do it. So I can just maybe dive a little bit here. So this is the architecture of the Gen 9 actually. So what you can see is that we are using the L3 for the Gen 9. So actually when we do the performance prediction here, the offload tax is basically 0 because the data is assumed to be at some point in the L3. So we can read it directly from the LLC. Okay, and then you have some local cache. So if you want to run the roofline, then you will have some information on the roofline on the different memories that you have. So you will have information about the L3 arithmetic intensity, the shared local memory, the aggregation of shared local memory plus L3, because this is actually the same portion of the memory at some point, and also the GTI bandwidth, which is the bandwidth for the accelerator here. So you are already able to extract that kind of information. So that's pretty useful because if you want to optimize here, for example, for this specific code, you see that you are already very close to the roofline for the shared local memory here. So you definitely want for L3 actually and shared local memory. So if you want to optimize this code on the GPU, the next step for you would be to find a way to reduce your memory impact or to try to reuse as much as possible the data directly from the L3. And then you would actually move this part to the right, which will give you more headroom to get more performance. So that's how you read it. You should have come yesterday. We discussed about it, for those of you who are not here. Okay? So how to run the roofline? I will not detail everything here. You will get the slides, so that just to give you the different command lines. So what is important is to add enable GPU profiling to some of your analysis. And also this is an experimental feature. So you need to export this advisor XE experimental equal GPU profiling. If you don't do it, you will not be able to run it. So, but you have all those information here. Okay, so now I can probably just show you some report. So that actually this is the report for one of the application, one of the lab that we are going to do this afternoon. So that's a code called ISO3DFD. So that's a wave propagation kernel. It's based on finite differences. So what we can see here, so that was running in 13 or 14 seconds on the CPU. So actually this code was not parallelized. So it's not really a fair comparison at some point, but at least you get those numbers. So it's up to you to know what you are doing here. So it was not parallelized. So it was I was running on a nuke. So that was I think i7 with 4 physical cores. So I could get some performance improvements definitely here on the CPU side. But at least I was just interested in getting some performance prediction for the GPU, for the Gen 9. And on this machine, I also have a Gen 9, so I'm also able to play with the Gen 9 here. And then, so that's basically what I told you. So there is just one loop that can be offloaded. And I can actually go to the offloaded regions here. So by default, if you don't select anything, you don't see anything. And then when you just click on one loop, actually, I can just show you here. Okay. So this is basically all the section, the cut section that you should offload. So that's fairly easy to understand it because this is the gray part. And so then your goal will be to find a way to put this on the GPU. So a very actually easy way to do it is to change the OpenMP parallel 4 to use the OpenMP target and to target the GPU. So you need to change some of those parameters to explicitly say what you are going to map, the memory that you are going to map on the GPU. But it's not that hard. So that's already, I would say, kind of working with our actual compiler. So the performance is not very good yet, but that's going to improve. For OpenMP, I'm just talking about OpenMP here. That's going to improve because I think that the goal is to get basically the same performance when you are doing this target on the CPU, because you can also offload the data at some point or target the CPU. And we are trying to get actually the same performance when you use the target on the CPU than when you are using the OpenMP parallel 4. So that's definitely going to improve. Otherwise, you can use actually data parallel C++, and what we are going to do this afternoon is changing this code to DP++. So you will see how it works. And this is actually a pretty advanced lab because we also play with the decomposition. So we kind of trick how we are putting the data on the GPU. Do you have questions?
Yes, so with DPC++, do I have to make any changes on the code, or are they supposed to become automatically changed?
No, so you need to make some changes, actually, because the way it works is a bit different. Yeah, there is a... Oh, so yeah, the question was, if I'm using DPC++, do I need to make some modification on my code? So yes, you will need, so you will understand that this afternoon and even this morning. So there are many things that you need to do to just prepare your flow. With DPC++, you need to set up the device. You need to create what we call queues that will be used to take the instructions that are going to be flooded and things like that. So there is some preparation. So this is really C++ based. So here, you know, this is C, Fortran, OpenMP that works with everything. So yeah.
Yeah. So one more question.
Yeah.
So currently, what type of GPUs are you supporting? So
Integrated GPUs.
Only integrated.
Yeah. So with DPC++, so far we are supporting Gen 9, Gen 11.
Okay.
Which are the Intel integrated
ones.
GPUs. So actually, I can also probably just answer to the next question. So which will be is NVIDIA supported, I guess? Or
NVIDIA or AMD.
okay. So we are developing our own compiler for DPC++, but Codeplay is also developing a compiler for SQL, and they will release, I think this is in March or April, a first version for targeting NVIDIA GPUs. So, and that's the idea with DPC++. So one single language, and you can target different hardware, not especially Intel hardware.
Okay, so and the last question that I have is that, so let's say the very simple scenario, I have my Python code, everything targeted on CPU, and I have my TensorFlow code within the Python.
Yeah, okay.
So, I mean, within the TensorFlow code, we know a priori that, I mean, the gradient should be estimated on the GPUs, the average of the gradients on the CPUs. Is it something that the offload advisor can give me automatically?
So offload advisor will be able at some point to profile it. So it's working with Python, but it's always more painful than native code. Advisor will be
use the C++ then.
Yeah, so that's the point. Yeah, because you have some libraries that are basically coded in C++ or that are native libraries.
I use the C++ and the TensorFlow library of C++. So if I write it in C++ and TensorFlow,
then that should work. Yeah, then that should work. But then for TensorFlow, I'm not a specialist in machine learning and things like that, but I guess you will rely anyway on libraries, and that's up to those libraries to do the offload on the GPU or to basically detect what
you assign by hand the actual device.
Okay, so you can do it already?
Yeah, you can do it.
Okay.
My question was, is it the offload advisor going to give me automatically?
So probably this is native language for sure. You will get those information, yeah.
Okay.
You have unit testing frameworks.
Sorry?
Unit testing framework for this language.
So
unit testing. How do you test your code?
So how do you test your code? I would say that this is standard C++ at some point. So you will test your code with any libraries that you are or framework that you are using.
There are unit testing frameworks like CPP unit and NUnit and so on.
You can still use it.
But how does that support your this DP C++?
So you mean when you offload on the GPU? So that will be actually, right now, I would say it's probably painful to do some unit tests directly on the GPU because you are on another context. So, and for example, you can't do directly printf or things like that. So you have a limited set of
like assert the data and verify the data.
You can do it after offloading, for example. So if you do some computation on the GPU, then you have some result and you want to check this result, then you can do it.
Yeah, which framework do you use? CPP unit?
Whatever you want. This is standard C++.
Yeah,
so,
okay.
Yeah.
Cool. Thank you.
Yeah, welcome. Other questions? Yeah, Georg. Yeah. Okay. So if you have questions about DPC++, we'll have a presentation right after the break. So.
Okay, thank you. Could you go back a few slides where you had shown the memory bound and compute bound?
Oh, I can show you it here maybe.
Examples.
It's
for memory bound. So you mentioned the caches, but you didn't mention the cache level. So what is assumed there? Is it last level cache always assumed? Can I configure that?
Yeah, this is aggregated here. I think that you might get those information here. I'm not even sure actually. Okay. Let me try to just start again. Okay, so actually you see here this is bounded by LLC bandwidth, but data transfer, count. Yeah, so you have information about the L3 cache here. You have information about LLC and for memory, you can check. No, I guess you won't have information about the other cache level.
Okay, so it's LLC then.
Yeah.
Okay, thank you.
Yeah, another question?
Just 1 second. Hold that question. So there is no GUI tool anymore, right?
No, not yet. So the GUI is this HTML page at some point. That will be integrated later.
Right, thanks.
So because we have a GUI with Advisor, that will be integrated later. No other questions? So we are going to use it actually this afternoon for Float Advisor. So we are going to run the whole process basically, starting from the CPU application, running offload advisor, and then offloading on the GPU. Okay? So I think this is a break.
Yes, so we've got 15-minute break now, so come back at 11:05.
So it's me again. Actually, we are supposed to be two, but my colleague had some visa issue and couldn't come, so you will have to, take a lot of me today actually. So we are going to continue with a first introduction to data parallel C++. Then there will be a lab also this morning, just a first, let's say, hello world, even if this is not a real hello world. Just before we start, I just have a question. So who is using CUDA here? Okay. So, data parallel C++. So this is the agenda. So there is an introduction, then we have this hello world with a lab. So the lab is pretty short, but I expect that we'll need some time just to connect everyone to DevCloud. So we should have enough time. And then I will go into the presentation of the language. So we'll go a little bit deeper so that you can understand basically the tips and tricks. So that's C++ based, you will see that. And there are good ways to program it and bad ways. I will try to show you some examples what you should not do at the end, basically. So, what is data parallel C++? So this is, I'm not really calling that a language, even if we are saying that it's a language, it's not completely true. Actually, this is based on C++. This is regular C++. And this is also based on the SQL standard. So SQL, this is developed by Kronos, and they are also the guys working on OpenCL. So initially there was a strong connection between OpenCL and SQL, and that's going to change. Actually, we are going to, we are also part at some point of the SQL committee. We are pushing some new feature in the SQL committee. So the idea is that we don't want to be blocked by SQL at some point at Intel. So we take SQL and we add some extension to it. And this is what we call data parallel C++. And those extensions that we are doing on our side, then we are pushing it back to SQL. So that's basically the idea. So this is an open standard based on C++ 11, 14, and 17. So you need to use some advanced feature at some point of C++. So who here doesn't do any C++? Okay, that's going to hurt for you guys. No, so we can try to, we will help you actually. So there are some specificities here with C++. So I guess if you're not doing C++, you are probably doing Fortran. Sorry? C, okay. So that's not that bad then. No, so if you are doing Fortran, you are most likely not directly interested to DP++, and for you, I guess, and in your position, the good strategy for me would be to do OpenMP, actually, OpenMP target. But here, this presentation will be about data parallel C++. So the idea, this is cross-architecture. We claim so far that it will be performance. So we are still in beta, so don't expect the performance to be right there. That's going to improve, of course. And this is open. So cross-architecture, that's exactly what I said earlier. So the idea is that we are developing our own compiler for targeting Intel hardware. But as this is open, basically everyone can implement its driver to basically run on any kind of hardware. So Codeplay is going to do it for NVIDIA, but we can imagine that in the future you will also have other vendors. So what's the difference so far between SQL and DP++? So SQL is providing all the basic blocks, basically. So you will see, we'll describe what are buffers, scheduler, You have many things here. And what we are bringing so far, the extension that is really part of DPC++, this is what we call unified shared memory. So you will see that with SQL, at some point it's a bit painful. Painful is maybe not the appropriate word, but when you need to specify what is going to run on the device, you need some work to do it. And you need to specify basically this data needs to be to go into a buffer, then I need to create an accessor. So you have several steps that take some lines of code. And actually, with unified shared memory, we try to make it much simpler. You just use regular pointers. So you use your pointers on the host. It will also be available on the device. And that's very close to standard C or C++ way to do the other thing. So that's the extension that we have so far. And also we have device-specific extensions. So for example, we'll have it for FPGA, and you'll get more insight with Karan this afternoon. So just before this hello world, what is important to understand is actually the lambda expression in C++. So we are using that a lot. So lambda expression, this is a way to define actually a function in the code where this function is going to be called, basically. So you have several things here. So first thing is the left part here. This is what we call the capture clause. So the capture clause, when you are running a kernel with SQL, there is something that is mandatory, is that you need to provide the data by copy. If you don't do it, that will basically fail. So that's just one of the restrictions so far. And then you provide your parameters, and then this is basically the function, the kernel here. Okay? So what does it mean here? So we are just basically creating a function that will be executed here by this sort here, and that just returns. So I'm too close here. So that returns the absolute value of our B or something like that. So that's just basically a function here.
No, I'm not asking about that. I'm asking about, you said you must use copy for all these captures. What does that?
Oh, you have different way to provide the parameters. So basically here, those parameters, if you specify the equal sign, it means that it will be a copy of A and B that will run into the kernel here. But you could also specify the so I don't know how to call that in English.
Reference.
Thank you. So and this will be by reference, but the sign I don't know. Yeah. Okay. So you can also specify that you want to get it by reference in that case, and that will not work for the kernel here. This is a restriction. We need to specify that this is by copy. Then you have the lambda body. Okay. So also for this presentation. We are using this kind of header here. So we are defining some things. So by default, if you don't use this using namespace, you need to add for every feature of the language, you need to add CL, cycle, many things after that. So we try to make it a bit simpler for the presentation here. So we just are using this namespace here, CL cycle. So it means that we're not using it directly in the code. But keep in mind that if you are doing your own stuff on your side, you will probably have to add it or use this using namespace definition here. And also, we are using some define here to the access modes. So I will explain later, but you will find basically those names in the code later. And those names stands basically for some namespace here. And also, what we are doing here, we compile with this option, which also remove one of the language restriction, and I will explain that in the next slide. So this is let's say the hello world. So that's not printing hello, that's just doing some computation. So that's a vector addition kernel here. So how does it work? We have basically two sides. We have a part of the code that is going to be run on the host, so the CPU, basically. And you can see that we have a part here and a part at the end. And then we have the part that is going to be run on the accelerator, and this is basically this part in the parallel 4 function. So let me explain what we are doing now. So first, we have some array A, B, C, and the first thing that we need to do, we need to create what we call buffers to be able to access those data on the device. The device that can be actually the CPU, it can be a GPU, it can be a FPGA, it can be whatever you want. But you need first to create those buffers. So there is something very tricky actually here. When you create those buffers, the ownership of the data, in A, B, C, goes to the buffer. It means that if you try to modify those data directly later, you don't know what is going to happen. So you need to be aware about the fact that once you declare this buffer, you don't want to play with A, B, and C in your code anymore, unless you destroy those buffers. When you destroy the buffers, then you're back to getting the ownership of the data to the initial arrays here. So that's the reason why actually we have those parts here. So it means that when we reach this one, then the buffers will be destroyed, and then we can use back the A, B, and C arrays. Then we need to create a queue. So a queue is basically linked to a device. So if you don't specify anything, like you just create that kind of queue here, SQL is going to use what they call the default selector. And the default selector might end up first, if you have a GPU, might end up on the integrated GPU. If you don't have one, then that will end up on the CPU. So we create the queue, and then we submit some commands to this queue. Now, once we are in the queue, we need to define accessors. We can't access the data directly from the buffer. So this is why I was saying that it's a bit painful, because you need to do both steps in the first place. And that's the reason why with the unified shared memory, you don't have to do those things. So here, this is the standard way of doing it in SQL. So then we create some accessors here. So actually, because of the scope, we can rename it A, B, and C, but you could call that A accessor or whatever. That's not a problem here. And then we need to call so from the buffer, get access. And this is where we are using those definitions that we were doing before. So usually this is SQL or CL, SQL, access, mode, read, something like that. The namespace is pretty large, so it's much more simple to do it like that. And you have 3 or 4 different modes. So you can specify that you want to access the data in the read mode, in the write mode, in read and write also. So if you are doing both reading and writing it. And then we have basically the part that will be executed in parallel. So we are calling the parallel 4. So we are calling it from actually the context here. And then in this parallel 4, we are just explaining what is going to be the operation applied to every element of the array. And every element of the array, this is basically specified here. So we have the range, and we are saying that this is a 1D array. So our problem stands in 1D arrays. 1024 elements, so this is what we have here. So here, we are basically passing the parameters by copy here. And here, this ID will be automatically generated by SQL, and will be provided with the good iteration number for all of these items. So you just have to basically explain the operation, and that will be applied to all of your elements at some point.
The ID.
ID, yeah.
Yeah, it is.
So
No, the ID. We have to use always ID or any other name.
You have also, so here this is the type of the data,
okay.
And this is the name of the,
very.
but you can use whatever you want. And actually you also have other way to get this information. So, and we'll use something else actually in the lab this afternoon. So that's basically it. And then once you submit this, that will start doing some execution. So you can also use a synchronization function at the end if you want to be sure that it will be executed before you go to something else. And then here, so we close basically this part, which means that at this stage, the buffers will be freed, and then we can access back the data and read the data. So I just want to show something also. So actually we can start by here. So by default in SQL, you need to name the lambda here. So you need to use this class and provide some fake name, vector add, vector whatever you want. So that's not important, but you need to put a name. And that's the reason why we are using this option for compilation. It removes basically this restriction. And then you can just use something that is more easy actually to understand. Okay? So actually I already explained some of the stuff. And so then we can read actually the data here. So what would happen actually if you remove those parts and you try to read it? So it will not fail, it will not crash. But depending on the device selector that you are using, you might get data or you might not get data. And we are going to play a little bit with that in a few minutes.
That's a quick question there. You mentioned a synchronization element.
We have, yeah. You can call actually, so here, what you can do, because actually this is pretty risky to do it that way. So what you can do here, you can use q.wait, and that will wait for the execution of the kernel.
So if you don't do that and you disrupt your buffers at that point, are you then potentially risking the...
Yeah, you don't know basically what is going to happen, yeah. This is just to give a very short example of what is happening here. And actually you can also create some, so if you want to generate your own exception, you also have the ability to call another synchronization routine, which is called wait and throw, that allows you to get some specific exceptions, so your own exception for example. Okay, so how does it work for the compilation? And I think you need to understand that for some tips and tricks that I will explain later. So this is a regular C compiler. So it will take your source file, compile it, and generate an object file. But then it will also pre-compile at some point this kernel here. And it will use different instruction sets. So there is POV. We are also moving to L0 at some point, which is something else. But this is some kind of intermediate representation here. Okay, so that's not directly something that you can execute on the device. And then we have the linker that takes all of those different elements and that creates your binary. And then when you write, the execution flow is basically you take your application, you start executing the code that runs on the host, and based on the kind of device that you are selecting for the device execution, for the kernel execution, then you can, from the runtime, actually switch to host CPU device. So this is basically host and CPU device. This is running on the CPU. So this is just different implementation of the driver for us. So for example, if you are using the CPU device, the implementation use TBB. If you are using the host device, I think this is just completely OpenCL based. So usually the CPU device gets better performance. At least for now. That will change probably in the future. And you can also select the GPU device or FPGA device or whatever kind of accelerator you have access to. So what you are going to actually do in the next lab is defining the selector. So I told you that we need to create a queue, and I will explain after the lab what is actually a queue. But when you create a queue, if you create the queue without parameters, that will just use what they call the default selector. And the default selector can be redefined in the environment, and you can select some of those different devices. And actually, by default, if you don't specify anything, that will try GPU first, then CPU if you don't have a GPU, and then host. And you can also actually directly select or generate the device selection in the code. So how do you do that? You can use those classes here, so GPU selector, CPU selector, host selector, and you provide it to the queue. and then that will automatically attach the queue to the device that you want to use. No questions so far? Yeah, question.
Is there a special selector for FPGA?
So that's a good question, actually. I'm not sure that we have, so Graham maybe can answer. So is there a specific selector for FPGA?
Yeah.
This is accelerator?
Yeah, there's both the hardware and the emulator, but we cover that this afternoon.
Yeah, okay, so you will see that this afternoon. I'm definitely not a FPGA specialist. So FPGA question, you ask Graham. Okay? So here, for example, we have an explicit selector. So let's try to connect to DevCloud now. So I guess all of you have access to DevCloud. If I'm not, if you don't understand what I just said, please raise your hand. Okay, so everyone knows what is DevCloud, and you all get access to it, right? So you should have received an email or whatever with some connection information, and if you're following basically what they are asking you, you should end up on this page. So I will just give you like 2 minutes, and you need to end up on this page. So who is already on the page? Okay.
What's the URL?
No, this
Also, the URL is devcloud.intel.com. Let me try to.
I think people need their specific URL if it has their login details.
Oh yeah. Okay. So you should have the URL actually in your email, in the email that you received from Intel. So. So just look at your email when you register to DevCloud, and you should get all this information. So who needs help here to connect to DevCloud? No one? So who is not connected to DevCloud so far? Okay, so let's wait a little bit. Just tell us if you need some help. So you need some help?
Yeah.
Okay.
Oh, okay.
So did you receive an email from Intel?
Yes.
Okay.
Okay. Yeah, I'll just go for it.
Just get your emails.
No. Yeah. Oh, okay. So.
Okay, so you are there.
Yeah, for the Intel.
No, definitely not.
Who needs help?
By this one.
Who is not
Yeah.
on this page?
This one here.
I got
Intel
this
DevCloud
email.
team. No, it's not
Okay.
now.
No, that's not the one. It's not from DevCloud. So maybe try to look for DevCloud directly if you have a search engine or something like that.
Yeah.
I didn't receive that email, only these two I got it.
So did you register?
Yeah, I registered yesterday.
So you did it yesterday?
Yeah, that's one. That's the email.
No, there was another link for registering
Yeah,
DevCloud. That's okay.
I didn't get that.
Okay, so that's why I got this.
Oh yeah, okay. So you didn't register to DevCloud, right? Okay, so then you need to follow basically so what is here, and the first page is this one. Yeah. And you need to go to Professional Research DevCloud events.
Okay.
And,
Then we can. Yeah. Thank you.
So everyone else is connected to DevCloud? So we are going to use Jupyter. Yeah. Okay, so we have still one access to our request for DevCloud. I can maybe start, and then during the break, I will help you do the lab. Okay, so once you are here, so you have actually, if you want to connect through SSH, don't do it now, please. You can get the information, download the key, do whatever you want, and so that's basically a regular SSH session. We are not going to do it because it's kind of painful to set up everyone, so we are just going to use Jupyter Notebook. And to do it, it's pretty simple. You just click on the blue button here. So let's do it. So let's make the flat crash.
What bandwidth you got?
You need to refresh the page.
So actually, you should be redirected automatically, but yeah, you see. So don't, actually, I think that if you refresh the page, you might create several instances of Jupyter. So yeah.
Okay.
And then you should be on something like that. So I might have some mess that you will not see on your page. But I will explain how to get more mess actually on your account. So who is not on this page so far? Okay.
Yeah, no, this is, should come.
Just wait. Yeah. Just wait. And
Yeah, log in.
Say 10 minutes.
10 minutes, okay.
Okay, well,
Yeah, we'll wait.
I'll come back in a few minutes just to check.
No, it should be redirecting you, I guess. Okay. That's really why I want to avoid SSH, because if you see already the mess just by clicking on one button and getting access to DevCloud, in SSH it would be even worse. Oh yeah, but you got SSH, yeah. No, but here, so maybe you can try to refresh it. Yeah.
Yeah.
Cool. Yeah, you have to just click on that thing.
So I don't know if the problem comes actually from the network here, or this is a problem from DevCloud, but so I need to wait for everyone to be at the same page, basically. Otherwise, we are going to miss some instructions. So does it work? Yeah. Okay. Okay, and it works? Okay, perfect.
And then
Yeah, no, that's fine. Yeah. It's not a big deal if you don't have, yeah. So who is not yet on this page? Feedback, yeah. So who is not yet on this page? Okay, so I'm assuming everyone is here.
yeah, just
So now be very careful and do exactly the same thing as what I'm doing. Okay, so we go on new here. Okay, and terminal. And then you need to execute something like /data. Oh, I'm back with my German keyboard. /data, and then this is OneAPI_workshop.
Cedric,
Yeah.
you can do a Control Plus a couple of times to get the font a little bit bigger.
Oh yeah. Let's try that. It's not working.
No. How do we get that?
So can you see it here?
Yeah.
Okay, try. And then you have a script called getTraining.sh, and you just run this one. So data/data/OneAPI_workshop.
we don't have a data directory.
You don't have the /data directory?
No, I just searched.
You got it.
You got the data directory?
I just typed in the.
I didn't include that, but it's there. So try that.
Because I think with like new accounts or something. So I only registered 2 days ago.
Yeah. Oh yeah. Yeah, it's there. It's there. Yeah. I
What did you? How did you get it?
So you should have it.
Is it back? Sorry, back.
Yeah, you need to complete.
Okay. So where's the slash? Okay. /data.
Yeah, you have it. Yeah. CD and CD to the OneAPI directory.
OneAPI.
Yeah.
Oh
CD,
yeah. Okay.
You have that.
And get training.
Thank you.
Okay. So everyone see the script? Okay. So you just run it. And it will basically copy all the content on your local directory. So you can't work from the slash data. And then if you go back to actually the Jupyter page, you should see more mess actually in your directory. So who did not get the data on his directory? So everyone has it? Okay? Perfect. Well, that was fast. I was expecting more time for that actually. So then you have several folders, and the first one, the hello world, is vector add. So you can just click on it. And then you have first dive into dpcpp dot something. And then we just open this one. Okay? So just give you 1 or 2 minutes, and once you are there, you can start. So by the way, if you want to download those stuff, you can just connect through SSH, so later at home or whenever you want, or during lunch, and then you can try to SCP. So actually, it seems that there was some problem today to do SCP, so maybe they just blocked the command on their cloud because there was some training, I don't know. But anyway, later you can just get all this content just by doing SCP on your machine.
Is that the issue with the local install of the dev kit?
No, this is not part of the...
What you referred to at lunchtime, if you wanted to run the dev kit with the examples, is that?
Yeah. You also need, actually, if you want to run it, to install Jupyter. But it's not a big deal. Okay, who is not yet there? Everyone? Okay.
I mean, data, it's not data OpenAPI.
Yeah, that's right.
This one.
Oh yeah.
That was I'm already in data,
Okay.
so I'm going to go into data.
Oh, you're already. Oh, no, so you yeah.
So
So
I'm
go back.
Off this
Yeah,
morning,
go back
and
to.
it's been running in the background, so I've only got an hour left. And
Go back one.
It's
because
here. So then you're in your local directory, and then you can do it.
because the cells are purposely not completely shielded. So you will need to
Slash data.
yes.
We're not making it.
One
So I
API
posted down the
underscore
stuff again, and that time
something.
does not.
Oh, the underscore is not working.
Time left on the.
Yeah.
It keeps on
Yeah,
decreasing.
just use tab and get
So I've only
training.
got 9:24 left.
Yeah, but I
So I can
know
Yeah.
remember it again.
what is this time?
Okay, perfect.
That's timing for the Jupyter session.
Doesn't make any sense. I mean, you're not limited. I mean, don't just ignore it.
Okay, let's see what happens.
Yeah.
Okay.
It shouldn't be.
So you have some text. You can read it if you want. I will not. I will just try to explain what we are doing. So Jupyter is not meant to run any C++. So there is a module actually, but it's not working with DPC++ because this is not a good LLVM module. So we are doing some tricks here to hide some mess and to simulate some kind of execution in a kind of nice way. So what we are doing is that every time, actually, instead of doing some kind of execution on the fly, we are writing files. So basically, we have this directive here that will create a file called dpc.h. And once we execute this command, that will create this file, put this into the file, and then we can do additional steps. So actually, it seems that there is a bug here. You need to put one more space, otherwise this file is not created. So just add one line at the end, and to run it, you can do Shift-Enter. And you should see something like writing dpc.h. Then we have, so this line here has nothing to do with this training actually. So this is just to provide you some way to reset the code. So you are going to do modification on the code, and so there was an easy way for me to provide you the code. It was just to provide you everything with comments, and then you remove the comments, you compile, that works. It's not the way I think that you are going to learn the language. So I'm not basically putting everything. You will have to go to the documentation and do some search at some point to complete the code. And the idea is that with this reset code, you can actually pass to the next step without completing the previous one. It will just recreate the environment correctly so that you can go to the next step, even if you don't complete one of the steps. I will go with you, but in case you have a problem, so just remember to execute this command. Okay? And then we have the first part of the file here. So we create some arrays, A, B, C. We do some initialization. And then we are going to create the selector and create the queue. So there is one restriction. If you want the code to work, you need to ensure that the queue is called queue. If you don't do that, then the rest of the code will not work. So that's up to you. So you can create a selector. So I might just drive you for this step here, and later this afternoon you will have to do it by your own. So what do you want to do? Yeah.
Maybe just reiterate on the how you go from one step to another, how you actually execute the cells within Notebook.
Yeah. So you need to do a Shift Enter on the cell, on the selected cell, to execute it. So the command was how to basically run a given cell on Jupyter. So you just click on the cell and Shift Enter. Okay. And actually, I think you can also click here. Yeah, run this cell on the side here. So everyone was able to do some execution of the cells? Okay. So we need to create a selector and then create the queue. So we can create different selectors. We can specify that we want to run on the CPU and the GPU. So that's up to you. I don't know what you want. You can try different things. So in my case, I will create a GPU selector. I will call it cell. Okay. But you might want to use a CPU selector or host selector. Maybe at the end of the day, I will get used to this German keyboard. Okay, and then you can actually create a queue. And if you remember what we've seen earlier, we need to provide, we don't need actually, but as we are creating the selector here, we provide the selector to the queue, and then the queue will be linked to basically the device at the stage. So if I didn't do any mistake, then you can execute the cell. So that will actually write the file. And then I need to explain what we are doing here. So you don't need to do anything in this cell here. This is just some internal mess. So basically what we are doing is that we are splitting the code into different files, which are called part 1, part 2, part 3, and part 4. And it's just for letting you do this step-by-step implementation. And what the script is doing is just merging all those files in one single file that we are compiling at the end. So at this stage, I'm already providing the part 2, part 3, and part 4, so your code will work if we didn't do any mistake. And you are at least able to see that what you did in this first step is working. So that's basically the idea here. And then this is also compiling and running the application. So let's execute that. And then we are just creating the script to merge everything, and then we are running it. So you need to execute also this cell. And on this cell, we are using another script, which is calling the batch scheduler to send actually the work on a compute node. So if I didn't do any mistake, then you should see some output here. And so this is working because we are just adding two arrays together that goes from 1 to 1000 and I don't remember something. And so then you see that you double the index basically every time. So everyone was able to run that? Okay, so we need some help here. Okay. So feel free if you need some help. Several of us can help. So.
Okay, so it means that, so can you go up? Okay, oh, you need an L here, GPU selector. And then, yeah, you need to, did you execute this one?
Yeah.
Yeah, and then you need to re-execute the other one also. This one also, and then this one. We can do, you know, from where. Okay, so can you GPU selector?
Go up again.
Oh,
No.
That is fine.
No.
maybe the reset was
That's it.
Ah.
Now tap down
Okay.
to execute.
That's what you did was correct. So, yeah, you see, so that was probably the reset
Now
because the
what?
first step is to copy the file in the current
Yeah.
Because this script is actually running on cloud. And each notebook, I think it has your information somewhere. So, right? Yeah. So it shouldn't be that hard to get that.
Too many windows, isn't it? Too many windows.
Oh yeah. It compounds inside the browser.
Just a comment here. So if you are connected in SSH, just log off. Otherwise, you might get some issue with the compiler. So you need just to be connected through Jupyter. Yeah. Careful with the feedback.
I have understood what happened. Yeah.
Okay, so we'll still have problem to get those vector additions done? No one? Perfect. So then we can actually move to the next part.
Yeah.
So the next part, then this is the buffer creation. Yeah. Wall time. Where do you see wall time? At the end, you mean? Okay. Oh, this is so I don't know what this is exactly, but we are requesting a compute node, and this is the output that we get when we get access to the compute node. So that it has nothing to do with basically what we are programming here. This is just getting the node and. So basically, if you look at this output here, we are submitting the job. So this is what we are doing with this script queue here. And then all these parts, this is basically the output of getting the nodes. And our work really starts here. So this is where we are doing the compilation. and then the execution, and then we have the output here. So I'm basically not responsible for what comes before that, and I don't know what it means, and I don't want to know what it means. Okay? So let's work a little bit more here. So we need now to specify the buffers. So you remember that we had A, B, C. So far we just created the queue and the selector. And now we need to explain basically to set up the buffers. So the buffers, you need to use your array as one parameter. And the second parameter is basically the size of the data. But you can't provide the size directly. You can't put like, this is I think n, you can't put n directly here. So you need to use a specific class for that, which is called range. So you need to do range, and then you need to specify the dimension. And this is 1D here. And if I didn't do any mistakes, so then you can actually copy it. So then you execute it. I will go back. I'm just checking that it works. So probably this afternoon, at the end of the afternoon, that will take much more time than what I planned for the training because I'm going to make a lot of mistakes. Okay, so that works. And basically you have the output, okay? So I can show you here. So you just need to use this range, one dimension.
Yeah.
And then you execute. So at this stage, when we create those buffers, then the ownership of the data, A, B, and C, goes to buff A, buff B, and buff C. So we can't access the data or modify the data anymore. So is it working?
Yes.
Perfect. Yeah, it's working here. Okay. Question. Okay.
So is it like there's a pre-filled file and then you're doing the same thing, or is it different?
Also, the idea is that all those cells that you need to fill, it's like this is the same file for you. We are just like doing the flow, and I'm just providing the bits that are missing, so that you can check actually. What I didn't want to do was to provide you the whole code with nothing inside, and then you have to do everything. And if you miss just one step, it will fail. You don't know where it fails, so that's easier to just introduce it like that, I guess. So let's assume that this is working, so you should still see the same output. So then I'm not asking you to do anything, actually, I'm just providing you the code here. So we are calling the queue submit, we are creating the accessors. So the accessors, they need to use the context. So the parameter of the accessor is the context. So this is really linked to basically the kernel execution here. So we ask for read for A and B, because we are reading them, and we ask for write for C, because we are writing C, basically. And then we have the kernel execution, so we are again using the context, h.parallel4, we specify the range. So actually this is the same way to do it as what we did before for the buffer. Then we pass parameters like copy, we get the index, so that will be provided actually by the runtime. And then we just specify the kernel here, which is the vector addition, so C of I equal A of I plus B of I. So that's just what we are doing. So you can execute it, you have nothing to modify here. Actually, you will do it later. So on the other lab this afternoon. And there is some issue. So what is the problem? Sorry? Okay, maybe, yeah. So you maybe need to pass a new line. So I don't know why sometimes. Thanks. So sometimes you need to put an additional line in the cell.
No.
Don't ask me why. So okay, so that's working. And then at the end, we just output the data. So it's a bit complex to understand the workflow like that. So at the end, you can go to the overall code section, and you have basically everything. And we are going to play a little bit with what is here. So I don't know if everyone sees it, but for the queue here in the whole code, we are using a GPU selector, meaning that this part of the code is going to be executed on the GPU, on the Gen 9 integrated graphic. So if we run it here, so let's create a file, let's run it. So you will see basically the output. Actually, we can also put the queue weights. It's not mandatory here, but we can put it here.
Is it mandatory for correctness in general?
Yeah, exactly. Yeah. So we can put you can put the weight actually after the queue submit here. And what we are going to do now, we are going to play a little bit with the accessor, the buffers, and with the selectors. So you see that here, the results, they are correct, right? We are modifying something. And then what will happen if we just remove those two here? So let's try it. So I'm just basically removing the scope for the buffers here. That means that at this point, when I'm trying to print a C, my buffers, they are not destroyed. And now we can try to execute that. And so if you don't destroy the buffer, remember the ownership goes to the buffer, so you can't basically access the data here. So you might think, okay, we can't access the data because this is the GPU, right? And we are running the rest of the code, so this part is run on the CPU. So, okay, that makes sense at some point. So what would happen if here we change, for example, with CPU selector? Meaning that we are basically running on the CPU, and then we are offloading on the CPU. So any idea? Who wants to take some risk here? So do you think that if we don't put the scope, do you think that it will update the data at the end or not here? We can try actually. So actually it works because we're on the CPU. And we can also try the host selector. And it also works here. So actually this is, because we are running on the CPU, it's not really a problem to do it. But the problem might happen if we are running on the GPU actually, on the device, yeah.
In general, I'm not specific to this example, but in general, if you try to offload a critical part of your CPU-based code onto the CPU selector, will it be accelerated by the CPU selector?
So if you try to use CPU selector, that will be accelerated by just some kind of regular parallelization. So actually this is the difference. So CPU selector, the implementation so far, and I say so far because that might change on our side, on our compiler, this is based on TBD. If you are using the host selector, then this is OpenCL based completely. So yes, that will accelerate because then you will use for loops with TBD. So I guess that answered the question?
Yeah. I was just thinking, is there any more optimizations coming to my application on top of what the C++ compilable as well?
So yeah, there will be some optimization. So you will get actually some vectorization. You will get all those optimization can be applied also to the kernel. And this is, but then this is specific to each device. So that's the idea. But of course, I mean, depending on the hardware that you are targeting, you will definitely have for real HPC application, if you want the performance to be the best for each device, you will probably have to maintain at some point a different kind of kernel. If the hardware are really too much different, there is no way you can get the best performance in each case. But at least the idea is that you can at least get some kind of performance already, and you don't necessarily need to do it. But for FPGA, actually, you will have to probably modify a lot because the way it works is completely different. Okay, so that ends the first lab. So everyone was able to complete it, I hope. So let's go back to the presentation. So I have 30 minutes left, is that right? Okay. So now I will just explain in detail all of the components here. So I'm going to start with what we call the software model, which is actually specifying 4 different models. So one is called the platform model, the other one execution model, memory model, and kernel model. So the platform model, this is basically how you select some kind of device. So it might be host, might be device, and we'll explain a bit more how it works. It's actually the next slide. Then we have the execution model. So the execution model, this is everything that is based on creating the queue, creating the accessors, and basically being linked at some point to a given device. Then we have the memory model. The memory model is a way to specify data that needs to be mapped on both sides, on the host and on the device. So that contains the buffer, but that also contains what we call the unified shared memory, and I will give you an example later with the unified shared memory. And then we have the last one is the kernel model, which is basically what are you going to execute really on the device. And this one, so for the kernels that we create, like when we were doing C of I equal A of I plus B of I, there are some restrictions. So this is a subset of C++. Everything is not loaded. Then we also have at this stage what they call ND range is basically the decomposition of the problem. So if you remember the range with 1064 iteration, this is this part here. And there is also this word here. So if you come, I guess, from the OpenCL, you know that work item. So work item, this is one single iteration in the kernel. But we'll talk more about that. So platform model. Basically, you have your TP C++ application. You have a part that is supposed to be run on the host, a part that might be run on the device. So the host part, of course, is executed on the CPU here. And for the device code, actually, what is going to happen is that when you create your queue and when you submit some work to the queue, so before even entering the kernel, the computation that you are doing, we are creating what we call common groups. And those common groups, they specify actually the accessors, for example. So when you create an accessor that is translated into some common groups that will be sent to the queue, and the queue is responsible for basically queuing all those commands and executing those commands. So that handles the synchronization, the data movement, and the user-defined kernels. So we create this common queue, and then the common queue is basically executed on the compute unit of the device. So when we say compute unit here, it means execution unit. For example, if you are using a Gen 9, it means cores or threads if you are using a CPU. So that's what we mean by compute unit, something that computes basically. So once you are on the device, you have access to some global and constant memory and some local memory. So I think I explain later what this is, what are the differences.
So something also that might be of interest, actually, when you start playing with DPC++, at least when I started a few months back, it was not really clear in the first place what kind of device I was really using. I wanted to know, actually, because you might say, okay, I want to run on the GPU device, then something happens, and at the end you have a result, but you are not sure that you really run on the GPU. So a very good way to test it is actually to use those functions here. So the device get info, and then you use this namespace here to provide a name, and actually it will output for the queue, and for the device attached to the queue, it will output what kind of device you are using. So when you create your queue, basically, you get the device, you call this function, and that will tell you on which hardware you are running on. So for example, if you select the CPU device, you might get something like that. If you select the GPU device, you might get something like that. And we are going to do it this afternoon. So I think I already mentioned some of those things, but this is basically how to do the selections of the device. You can also create your own selector, actually. So you just have to create the selector and to return basically one index. And you can get this information actually from CLinfo. So you can use CLinfo to get the different ID of the devices. And then if you have a device that is not actually available so far in the default devices, then you can create your device selector and return the index of the device you want to target. Then you need to be sure that the driver exists also. Don't try to do it with any device. If this is not an Intel GPU or CPU, or maybe FPGA at some point, then it will not work. So execution model now. The idea of the execution model is basically to create what we call the kernel instance. So the kernel instance, this is basically one kernel object, which is what you are going to run on your kernel, so the operations at some point. And also the decomposition, so I'm calling that domain decomposition because this is something that is more relevant in HPC, but that's kind of the same idea, so that's what we call here ND range. And then the workgroup decomposition. I will show you right after that what is workgroup, work item, and all those things. So all those comments that are part of the kernel, they are queued. They are also put in the command queue. So as well as the accessors, actually, that we did before. It creates what we call work pool. So you might have several work pools, and then those work pools are going to be executed on the different compute units. So that's basically how it works. So you can actually have synchronization with kernel functions. So you can use barriers to create synchronization between work items in a work group. So you will have probably more, you will understand better what is a work item and work group later. But you don't have synchronization actually between work groups. So work groups, this is basically some parts that are splitted on your problem and that will run in parallel. And a work item, this is just a single iteration. So a work group contains many work items that will be run by one compute unit at some point. So you can't do synchronization between those work groups. It means that you need to be at some point massively parallel when you start creating those work groups. And you can also have synchronization between host and device. So this is what I showed you with the wait function earlier. So buffer the restriction, we already mentioned that. So you can also create your exceptions. So I will not spend too much time on that, but you just need to know that it's possible. So the kernel execution model. So this is where we explain what is basically ND range, work group, and work items. So ND range, this is a way to specify the size of the problem. And you have actually different ways to do it. So you have what we call the global ND range, which is basically the global size of the problem. Like
you have, I don't know, arrays that are 10 by 10 by 10. That will be your global work size, 10 by 10 by 10. And if in this 10 by 10 by 10 you want to do some small blocks of 2 by 2 by 2, then that will be what we call the work group. So you can have at the same time a global ND range that will define this size and a local ND range that will specify the decomposition of the work problem. And then within this decomposition, within this work group, each element is called a work item. So there is some kind of example here. So if we have an image, so with those given sizes, so the global size here means the overall number of iteration. So this is basically this multiplication. So that's 2 million pixels. So that's our global size. The only thing that you need to specify that is mandatory at some point is to specify the global size. You don't have to specify the work group size. It's an additional option. You can do it, but you are not forced to do it. So this one, at least, you need to specify. And that makes sense. You need to specify how many iterations you have. Okay. So maybe I can just, I think that there is, okay, so I can just explain this one. So the way to do it with just the mandatory option is to use that. So we just specify actually the range of the overall problem. And then, so this is two-dimension problem here. And so then the item here, the ID here, will be provided by the runtime with directly the information of the iteration location in this 2D space. If you want to be more precise, to do some, to get more control and to specify the size of your blocks, basically, into this whole problem, then you can use the ND range. And for the ND range, you need two parameters. The first one is the overall problem size. So that's basically what we were using here. And the second one is your decomposition, so the size of your work groups, basically. So it means that in each work group, you will get 8 by 8 work items. So I'm trying to reuse the vocabulary so that, so if you are lost at some point, if you need some more explanation about work group, work item, global size, just feel free to ask.
So the
It makes sense?
block is simply because of the hardware that it's of the particular GPU.
So you mean here?
Yeah.
So there are some restrictions. So you can't create more than a given, I think, so I can actually go to the next slide. It's probably maybe not the next, but there are some restrictions. You can't put any size actually for the work group. So I think you are limited into a given number of work items per work group.
Is that a hardware thing or?
Sorry?
Is that the hardware of the GPUs putting that restriction?
It might be a restriction that came from the hardware, but this is also part of the language because then the compiler will fail if you try to do some strange things here. So for example, I think, no, the compiler will not fail actually. So that's a runtime, you get a runtime exception. So here it's the same, so you need to guarantee that you have correct multiple of those sizes, otherwise that will also fail. So that's one of the restrictions, and the second restriction is about the number of elements that you have in your work groups.
I'm presuming there's an API that you can query the device capabilities at runtime.
So if I recall correctly, because I did some tests, we can do actually the test later this afternoon on that. But this is, you have a runtime exception. Because actually in the ISO 3DFG, so maybe not the version from this afternoon, but we have the ability to provide the size for the work groups as runtime parameters. So actually it doesn't check, you don't have any checking at compilation time. So, and this fails if you provide some work group size that are not multiples of the global size, and it also fails if you put too many work items in your work groups.
So the question is how to verify what is possible.
Oh, so you get, I think you can get the information with CL info at some point. Otherwise, you have some functions in the SQL standard that gives you the maximum number of work items per work group
and all those specifications. So you can get it directly from the, yeah. So that's what we are using actually for also outputting the name. So you have many ways to get information from this get info. There was a question also.
Yeah, I was just kind of mentioning a few colleagues to last time we were
So.
You kind of just mentioned like the ones to specifying the design yourself.
So what would be the interest?
Yeah.
So the interest is that it gives you more control, and it might be easier to adapt the size to a given device. So for example, for ISO, so the code that we are going to use this afternoon, if you want to get the best performance out of the implementation, you need to play with those sizes. And usually, so those sizes, for example, for the CPU, you want to make sure that the first dimension is appropriate for vectorization. For a GPU, that might be different. You want this size to be pretty small, like a multiple of 4 or something like that. So it's not the best option. Yeah, you can get better performance. It's not necessarily like you will get a crazy better performance, but if you want to do some fine tuning, then yeah.
Sorry, in the first example, you let the compiler determine it by yourself.
Yeah, exactly. Yeah.
How can you ensure it's visible? How the ranges are visible by the size of the bits?
So that's a good question. Actually, I don't know if you have some. No, you don't have any. Yeah, you don't have any restriction on the global size. You mean? Yeah, you don't have any restriction. So I don't know how it's handled.
Say that one
dimension
should be divisible by 8.
No, what is requested is that when you are using the local and the range, those numbers here divide those numbers here.
Yeah. So what is the first number as a prime number?
Yeah.
It will be 1 by 1.
You can use 1. That's your work. Yeah.
A stupid question.
There's no stupid question.
ND range of brackets 2. What precisely does that mean?
So where do you see that?
In the second one, both loops.
Yeah.
It says range.
Oh, so this is big because this is a 2D problem. So we have 2D arrays.
Oh.
Yeah. And you can use until 3. And then actually that changed the way you get the information from the index here. So then you have a 2D basically index at some point.
Is that 2 is necessary because we are providing 2?
It's not necessary.
Yeah.
So actually, it's not necessary. It depends what you mean by not necessary. So actually, your 2D problem might fit in a 1D array, right? In that case, that will be a 1D problem. But if you are using 2D arrays, then that's better to,
Yeah, my question is like, is it necessary to give the 2 because we are giving 2 parameters there for the dimension.
Yeah, I think
from there it can detect it automatically as a 2D array.
Yeah, but I think that the compiler will try to
specific.
Yeah. We can try actually.
Yeah, like the other C++.
Yeah.
Since we have the control now of the devices, could we actually process the image half of it on GPU and half of it on CPU? For example, if we are about to add +1 to each and every pixel.
So you might be able to do it, but then you need to add some other parallelism on the top of that, like splitting your work first, then having like a task doing some stuff on the CPU and sending some.
Split then the image and then distribute the image and then. Okay.
So I didn't try it, but I know that some people are trying to do that kind of thing. So.
Then this computation should be independent.
Yeah, definitely. Yeah. So we still have 10 minutes left, so I will just try to go forward. So yeah, this is actually, the restrictions are here, so you will get the slides. If you have questions, feel free to ask, but you need actually to get some multiples for the local sizes. So let's move here. So also actually for the kernel, you can't use
every C++ feature. So you need to use actually what is in green here. So you can use template, classes, overloading, but there are also some things that you can't do within the kernel. So you need to be aware of that. Anyway, if you are not aware of that, the compiler will let you know. So, okay, so there are also ways to, so you can use it directly in Lambda. If you don't want to recreate your Lambda every time, you can actually create some variable that will store your Lambda. You can also use functors. This is the next slide. So you have different ways to provide a kernel if you want to have, let's say, a more object-oriented way to do it. So it's possible to use functors. Just moving pretty fast. So the memory model, I told you that there are different memory that you can use. So there is the global and constant memory. So the global memory is basically accessible to all the work items. So that's basically what we are using when we are creating our buffers here in the previous examples. Then you have constant memory, so you can also specify actually that you want the data to be constant, so that you are not going to modify it. So that can give you some speed up in some cases. Then you have the local memory. So the local memory is basically shared between the work item inside of a single work group. So when you do your decomposition with the ND range, basically if you have two different ranges, then the variables are just visible inside the same ND range, basically the same work group, right? And then you have the private memory. So the private memory, this is just visible for a single work item. So how does it work? It means that inside of your kernel, in the parallel 4 execution, for example, you just create a variable, float A or something, and then that will just disappear after this iteration. So that's just visible for this given element. So I will just, so I guess you understand the concept here that we need to create buffers, accessors. So I will go pretty fast on this one. And anyway, you are going to do it again this afternoon. So at the end, I guess you will get it. So unified shared memory, yeah, that probably makes sense to introduce that. So unified shared memory, this is actually the extension that is not part of SQL. That is really part of TPC++. And I think that better than any explanation, what I can do is just showing some example here. So that was actually the old way. So you remember that in the first case, we are creating this buffer and the accessor. So we have plenty of stuff just before being able to enter here and do the computation. So with the unified shared memory, what we are doing is that we are replacing all those buffers, accessor stuff, just by calling malloc shared function. So we specify the size. Also, you need to specify the device and the context. And then you can actually initialize your data on the host. You can run on the device. And you can get back your data also on the host after the execution. So you see that it makes the code much simpler here. Yeah, question?
You need to do a delete then?
Yeah, you need to do a delete. Yeah. But this is just, let's say that the delete is right after. We didn't have enough space to show it. But yeah, of course, yeah, you need to free the memory. Yeah.
Does the get device function gives you where the buffer will be created?
So the get device function will actually specify to this malloc shared that the data needs to also be available on the given device.
Does it mean it will be copied, or does it mean the buffer itself will be only created once on the device?
So yeah, it means that at some point you will have, I don't know how it's implemented behind, but I guess you have all this creation of buffer and accessor, but this is transparent for the user. So you will have the same concept. So actually, you can also specify, if you want to copy by yourself the data on the device, you have some functions for that, so you can also do it. This is also part of the presentation. You will get it in the backup slides. So you have some examples how to basically copy by yourself the data on the device and how to really manage the memory by yourself.
Is there a performance cost with using shared memory on the current generation?
I have no idea for. So I guess that there should be no difference in performance if we compare this implementation to basically what we are doing with the accessors. But yeah, I didn't test it so far. So
or limits on the amount that you can allocate?
I don't think so. No, it will be the same limit as what you can do also with the buffers and.
I'm sorry.
Yeah.
According to the question the colleague asked about splitting the parallelism into CPU and GPU, can we create two queues or three queues, and one will use CPU selector, and the second and third will use CPU and GPU, and inside of the first queue we will have two queues that make some operations for half of matrix and another for the.
So yeah, you might be able to do it, but I guess there are some restrictions. So I'm not sure you can create actually two queues affected to the same device. I'm not sure. I can check that and go back to you, but I guess there might be some issue if you try to do that. Because you are going to try to send command groups from two different queues to the same device, and that might probably hurt.
So if you have support for NVIDIA GPU, then probably I will be able to run.
Yeah, if you have different devices,
CPU,
yeah.
Integrated and split into integrated and NVIDIA.
I guess so, yeah. I guess so, but then that's up to you to separate the problem and also to handle basically the parallelism for just putting your task on the different devices. But I don't see why you would get any restriction on that, as long as the devices are different. Yeah.
Do we have any how much memory?
So you might have some actually, and you probably, if there are some, you probably get it from the get info. Yeah, then I mean, there is probably no chance you can allocate more than what is available on the device anyway. So yeah, but you can probably get this information from the device get info. Yeah.
So we have CPU selector, but can we select, for example, we will have more than one CPU on our board, motherboard. So the question is, can we select which one we want to use?
So actually, not really. So it depends. The thing is that the CPU selector so far is implemented with TBB. So if you have a parallel for loop in the command in the queue submit function, then that will use TBB parallelism to split the work. And so far there is no control for TBB. So even if you are trying to use actually TBB features to control the number of threads or to control like the static mode or something like that, it will not work. So this is not available so far.
So for multi-GPUs, that they need to be actually
you need to get you need to get different devices.
Shall be getting different devices, but if I do a parallel table there or a parallel map, it's going to be parallel on the course of a GPU or parallel across the two GPUs?
I think so far you need to do it by yourself. You have to specify it by yourself. I'm not aware, I don't remember anything. I can check actually and go back to you with more details on that, but I don't recall anything that would allow to basically share completely the data on two GPUs.
Yeah. One last question that I have. So with the CPU, you said it's agnostic, so it will actually go and you cannot control the number of CPUs.
Yeah.
If you have two different servers, is there any way to orchestrate the CPUs in order to parallelize across different servers?
You can use MPI in that case, on the top of it.
Yeah, okay, so if I use MPI, then it will be, okay.
Yeah. So you don't have any restriction on that more than what you already have with HPC applications. So,
I think there's a concept on load balancing. You can assign CPUs to share the work. there is an option, I think, but I don't know how to do it.
No, so actually, yeah, you can, and that's the reason why it's also interesting sometimes to play with work groups and to specify the decomposition. It's because it provides you more control on how the data is going to be splitted across the different compute units. So, but so far, yeah, this is we don't have a lot of control, at least on the CPU. And we can't, for example, bind a given core or something like that. So what you are doing so far with OpenMP, for example, OpenMP Parallel 4, and when you want to specify that you have, static or something like that, and you want to bind, for example, the first thread on the first core, the second thread on the second core, you can't do that so far. But that will probably change actually. So remember, we are still in beta. So. And actually, if you have feedbacks like that, this is definitely interesting for us. So write us email asking those questions, because then we can also forward those information to the engineering team, and they can see that there is a request for that. So we definitely need your feedback on that. The beta is really the opportunity for you also to give your comments and to tell us what you need. Yeah. So if you have multiple GPUs, that's the question. Multiple CPU? So actually, in that case, I guess you need to create your own selector. And you can see it actually. If you see like on a two-socket system, I didn't try actually, because so far we are playing with hardware that has a Gen 9, and it means that this is not server so far. It's just like Nuke or laptops. But I guess that on a two-socket system, I don't know what CL Info would provide, but I expect that you see the two different CPUs. So in that case, you can create your own device selector and do it by hand. So you are using your own device selector to affect on one given side or the other side of the two-socket system. I guess it's doable. I didn't try, but I don't see why it should not be feasible. If you can see those different CPU with CL Info. So I'm just going to this part here. There are really two things I want to mention. I already mentioned this one, the buffer. So just don't forget those stuff here. Otherwise, you won't get synchronization of your data. So ownership will not be back to the data. So that's the first thing that is very important. And there is another thing that is pretty tricky, and that is also very important. And then I guess we can stop and go for lunch. Check, yeah. So this is this part here. If you do this, this is basically the wrong way to do it. So you create the queue. When you create the queue, the context is created. And when the context is created, basically this is on a given context that you will have the just-in-time compilation for compiling your kernel to the device. If you do this, basically every time you do one iteration, at the stage you basically destroy the queue. And when you are back here to the next iteration, you create another context. You submit something, then you recompile the kernel. So every iteration you recompile the kernel. So you can try to do some VTune analysis on that one. You will not see your computation, even if you have a lot of computation. What you will see is some compilation. So that will take most of your time. So how to do it? It's fairly simple. You just put the queue creation before your for loop here. So you try to put it as high as possible in your code, basically. And when you do it, then the context is created here. You pass the context to the queue submit here. And the first time you are going to execute, then you will have a compilation that will just be linked to the context. So you won't have the just-in-time compilation every time. So just remember that, otherwise you might get some serious performance issue. Do you have questions on that? You want to go for lunch, right? Okay, so thank you for your attention. And then we have more labs actually this afternoon. So that will be mainly labs actually. So I'll stop talking. Thank you.